So we are happy to have Dr. Torku here with us. So Dr. Torku, we has started this idea on this deep data-driven epidemiological models or dynamic models that he started working on. I think your first paper was in 2021. 2021, and that was a paper that also kind of also motivated this kind of work that we also starting here as well. To him that actually I remember talking about the ability to extend to some other type of dynamical systems, not just compartmental or stochastics, and some other stuff. And then actually since then he's gone ahead to do some other dynamical models that are not just ODEs, but different type of differential equations. And yeah, graduated recently from his PhD, and now fully employed by Morgan. Visiting the Almeida, and then I said, okay, I want to invite him to come and give us and talk on some of the things he did. Once he's left academic life, since all the things that he's done is going to zero. But hopefully, I mean, we'll be able to get Ghanaian students and Ghanaians to kind of pick up some of the knowledge he developed during his PhD and as it's a new area that is now kind of hot cake. It's a new hot cake area to be able to use mathematics and data science combined. And I also think is really important, an important area as well. So thank you very much, Doc. And like, by the way, he's an alumni of DCC. So
I was here some, and also I was a TA for Dr. Mahmoud and Professor Cancer and Cancer's wife. So I was TA, I was in that office. Very much, Professor Mo, for this opportunity. I want to acknowledge my PhD advisor. In fact, he actually told me that I should do something like anytime. He has this good heart. He's from Pakistan. It's called Professor Abdul Khalid. It's a good man. That's one of the blessings I had during my PhD study. If you get a good professor, you are good to go, whether at the master's level or the PhD level. So a big shout out, although he's not here, but I want to really truly acknowledge him for the yeoman's job he did. It was almost 5 years plus of my life in this thing. So let me go into it. Let me go into the meat of the talk, and I'll try to go high level and stress on some. Okay, I should use this one. Yeah, this one. Yeah. Okay. All right. Thank you. So this is going to be a synopsis of my talk. I'll just briefly introduce why do we need to use deep learning for differential equations. And by getting that basis or foundation will help us to explore more. And then I will introduce the challenges of neural networks, for which it was obvious someone and Emmanuel, some of these things will help them. And if you want to explore this space, understanding these challenges will go a long way to help you build very good models. So let me get into it. Why deep learning for differential equations? There are a lot of numerical methods that have been built and developed that are used to solve differential equations. you can talk about the popular one called an Euler method. If you take a simple first order differential equation, you can use the Euler method, and so many variants of good numerical methods have been developed. However, there's a problem we run into, which we call the curse of dimensionality. What we mean by the curse of dimensionality, when the the dimensions become extremely large, you're looking at a lot of variables. Here I'm talking about variables, the first differential equation, the second differential equation, third, fourth, and a number of these equations that lead to the system differential equations that the traditional or conventional numerical methods aren't able to do a better job in finding the solutions to this problem. And then when it comes to time-dependent parameterized models. So again, our two speakers, Samuel and Emmanuel, if the model they have, they extend it to time-dependent parameters, traditional methods fail woefully. But thanks to differential equations, thanks to deep learning, we are able to handle these complexities because of the computational resources that we have at the moment. Number two, deep learning models are data hungry. They depend more on data. So as these parameterized models expand, we are able to leverage on the computational resources that deep learning bring to the table, and we're able to solve them. And then again, the third point ties into the second one, identification and learning of these parameters. So if you are just solving the problem, for example, you are learning the susceptible class, it's called a forward problem. But if you are learning the parameter, say beta, the Americans say beta, sorry, then that will be inverse problem, okay? And then the issue of when the problem becomes very complicated, and so many intricacies within the problem. We have high dimensional data. And the good part is, with the advent of technology and this machine learning stuff, we have a lot of leverages from deep learning, wherein the traditional methods fail woefully when it comes to high dimensional data. When I did my internship with the company I'm working now, I discovered that classroom work is nothing when I was dealing with a high volume of data, and you have to analyze this data and really have a feel of what it means to be dealing with real, actual, large data. Thanks to the advancement in machine learning AI, we can handle all of this. Now, many companies, I don't know about Ghana, but from the US, they produce terabytes. I don't even know the size to give. They produce a lot of data every day on a daily basis. And so the advent and the advancement in technology has helped a lot. So deep learning is really good for differential equation, complex dynamical systems, and of course, for high dimensional partial differential equations. So I have at this point set the base for you to understand the need for the use of differential equations. Deep learning as an arm of machine learning. So deep learning is a progression from machine learning. Traditional machine learning made use of what we call multi-layer perceptron. He started from single layer perceptron, and there are many other machine learning models. But the single layer perceptron wasn't producing the results that researchers and modelers wanted to see. So it was like, okay, they moved to multi-layer perceptron. So back in the days, we had not had that advancement we have right now in terms of GPUs. How many of you know GPUs? We have CPU and GPUs, okay? So in terms of the processing speed, all we relied on was CPUs. And CPUs really took a long time to even run a very simple model. So when GPUs started coming out, like, oh, we can now increase the layers, okay? Now, not only one layer, but we can go to 2 layers, 3 layers, 4 layers. And so researchers started asking questions. Wide versus deep, I will explain. And that is where I get something like sensitivity analysis. I'll talk about that. So fast forward, the field of deep learning started gaining traction, and people were like, wow, deep learning can do amazing stuff. One of the first type of popular neural network we have is the feed-forward neural network. It sort of goes from this top-down approach. My two speakers have already touched on that. So everything they talked about is basically the feed-forward neural network. Okay? I don't want to belabor much on that. Let me go to another type called the residual neural network. It's called ResNet. Okay? So the ResNet, over time, one of the challenges that feedforward was running into is that when the complexity becomes huge, there's what we call a problem arises called the gradient vanishing problem. So everything was turning into 0 and negative, like the gradient was vanished. And let me go back to a retrospect. So in neural network, when you do a forward pass, you have to do a backward pass. In the backward pass, since I'm talking to mathematically inclined people, there is what we call a backward propagation. It goes through what we call a chain rule that from the output up until the first layer, there's a process of optimization going on. It uses the chain rule. And because it uses the chain rule, there's this gradient element going on. Now, when the parameters become large and we don't know how to handle it very well, they tend to go to 0 very, very fast. And so to address this problem, these researchers did residual neural for image. It became a very popular type of net because it was solving that problem. What it did briefly was, hey, instead of, let me use this to explain to you. So we are moving from the input to the output. That's what we call a skip connection. So we skip some hidden layers so that the process of optimization and convergence will be faster when you are dealing with large volumes of data. Now, if you look at image data, just one image data, and you compare it to pixels, and then the numerical values come out, you discover that a lot of data for only one image. So that was a problem we ran into. And residual neural network at that point solved that problem. So think of the forward Euler or the simple Euler method. You have the y1 equals y k by k, substitute k plus the right hand side. Now, that's the same thing we're looking at here, where the neural network of the neural network data together parameters of the model. All of them will be embedded in the data. So it's a very pretty powerful architecture. It can be nowadays we use a lot of Arima 4x. I should share it. Okay.
No.
Oh,
Click the.
oh, this one. Okay. Okay. The next type is the long short-term memory. But before I do that, I'll talk about recurrent neural network. There's also the issue of sequencing, sequential data. So when you have data that involves time. So this architecture. Long short-term memory came out as a very powerful tool vis-a-vis this neural network that also solves the vanishing gradient problem. What this architecture does is that it looks back in time. So it looks at the past history of data. So let's say t minus 1, t minus 2, t minus 3. It goes back in time to be able to predict t plus 1, t plus 2. That's how this long short-term memory works. This architecture has what we call 3 major gates. We have the input gate, we have the forget gate, and we have the output gate. You can read more on that, but the main idea of this is that there's this hidden state that takes care of the previous information, and then it has activation function that ensures that only the is part flow of information gets any unwanted information to be able to predict the right stuff. So think of it as it uses a forget gate to filter and to give you the right information, because there's a lot of chunks of data that is being fed, and within the mind of the architecture is trying to find the right information to take it to the next, to the next, to the next. So all irrelevant information will not go to the next. So think of it in that high level view. A variant of the recurrent neural network is called the bi-LSTM. So it is original LSTM looks kind of, think of it like the feed forward. It goes one way, but the bi-LSTM, because over time the LSTM was running into performance issues. So to improve upon the performance, although this also comes at a cost, because once you go through the forward layers, you have to come back through the back layers, which will take time before it gives you the output, right? It has its issues when it comes to time in terms of speed, but performance-wise, it's good because it traverses almost the data twice. So it's able to give you something very accurate. So it is relative to LSTM, this is better. But of the 3, the one which has proven to be both in terms of performance excellent and speed is Guru, we call the gated recurrent unit. So what this does is that, unlike the LSTM, it has 3 parameters. And so one thing you should understand, when the parameters increase, your model has to run through all of them. So computationally, it takes a lot of time and resources. So this was developed as an improvement on, again, the LSTM and the bi-LSTM. So this only has 2.
This is your progress.
I truly appreciate those who are patient on the online. Please, all of you online, we appreciate your commitment. Our internet connection. I want to run the long connection. It's very important. If you are dealing with classification problem, you don't go and use MSE. There are binary classifiers, losses that you have to use, like the cross entropy. So the choice of the loss function is very important. Whether to use NA, mean absolute error, mean squared error, and whatnot. And how these predicted and the targeted differ is what we call the loss function. So you are trying to get to the global minimum as fast as possible, but also in an optimal way, so that there's no overfitting or underfitting. How about the optimization techniques? There are standard optimization techniques like the Adam optimizer. Did you guys use the Adam optimizer? There's also what called the stochastic gradient descent. We have some variants as well, but the popular ones are the Adam optimizers. So the choice of these also poses a challenge. How about the learning rate? So somebody will start with, so the learning rate is how fast you want to get to your global, somebody has asked a question, I think. Okay. How fast you want to get into how fast you want to get your global midpoint. And then the activation function. Now, the activation function is really important because, like Samuel rightly said, there's a lot of non-linearities within the model as well as the data. And so you have to ensure you choose the right activation function. So let me say something to Samuel. For differential equations, from my experience and others, the right activation function has to be chosen. The ReLU has not proven successful for the type of work we do. How big the tan hyperbolic function has proven very successful. You have to apply it on both the hidden, you can apply it on the hidden layers, and then on the output layer, you can apply the sigmoid function. So that gives you something within 0 and 1, and then you can, I'll show you a data processing technique you can use. So that you have 0 and 1, and then you recast it or rescale it back to the original data. And then regularization. Overfitting is a major problem when it comes to these deep neural networks. And so there's a need to be able to use the appropriate regularization technique to avoid, as it were, overfitting your problem. Now, I'm going to run quickly because of the network data-driven simulation that I did in my PhD work. I'm glad to say that 2 of my works have been published. I still have 1 to get it done. My professor has told me, but I've been busy. But I'm really grateful that my work, majority of them have been published. Well, before you feed the data you have to the model, you have to the neural network, you have to do some data pre-process, and that's the first step. So those of you who want to do data science, data pre-processing step is very, very important. If you get the data in the right format, your architecture should do pretty good. And then having the knowledge of hyperparameter tuning will also help you overall to get a better fit of the model. So the process of transforming the data into a useful format, these are the 4 main steps. You can skip them as you want, but you can also merge all of them together. One of the things you have to do is to handle missing values. Missing values are really important. If your data is full of missing values, then it's going to affect your results. And then data integration. Sometimes you are getting the data from different sources, so you have to get folders that you store your data. And in this day of cloud, I'm not know AWS, Amazon, something, yeah. So one of the ways you can do is also store your data in AWS and have a seamless connection between that and your model. And then data specification. You specify the features you want to use. Like Emmanuel used the Ghana data. So you have to specify, okay, I'm looking at only the vector column. I'm only looking at the recovered, right? I'm looking at the number of dead. So you have to specify, very important, so that, and then finally you transform. You can transform the data using the following techniques. These are not the exhaustive techniques. There are a lot of them. You have the Z-score. You can put it in a normal distribution. You can also put it in a min-max scaling form where you have 0 to 1. And then you feed that. And let me talk about the left and the right censoring. So the left censoring is that when, for example, when COVID was playing out, right? You have to ensure that at the beginning of you have the right amount of data at the beginning of the start of your model. Right sensing, on the other hand, is when, for example, vaccination came in, right? So the issue of vaccination came in. Now, how do you incorporate that into your model? So when there's an element of a change in the data pre-processing or the modeling, how do you accommodate a change as the right censoring? Cross-validation. So after you have processed and basically you've done the modeling, there's a need for you to validate your models. And one of the ways to do that is a cross-validation. Now, cross-validation tends to be useful when you are comparing different models. So you are looking at maybe random forest, you're looking at PINN, you're looking at least square regression. You can do cross-validation to assess or to accept which of these number of models you are using is the best if you are looking at 3 or 4, or better if you are looking at 2, right? Random splitting is a process of random. So one of the things you can do under the cross-validation is to split the data randomly into different folders. And that's an algorithm for that. And then for each of these split, you create a train and a test set. And one of the test sets will be used to validate the model at that k-fold. Okay, fold 1, fold 2, fold 3, fold. If you decide, and I took this idea from one of the popular books on deep learning. The guy said, as a rule of thumb, You can use 4 or 5 tables, 4 or 5. But again, this is dependent on you as well. Once you start seeing a pattern, if you are using three fold, 4-fold, 5-fold, and you see a pattern, you can basically have the RMSE for each of those k-folds to be able to make a good judgment. So from all these k-folds, you get the average results, and then you average that, and you put it down, and you do it for the next model, and put it down. Okay, then you can use what I'm about to talk about, what we call the error matrix. So what we are doing in this sense is regression. So under machine learning, deep learning, there are 2 major areas. We have the classification and we have the regression. Even though you hear logistic regression is a classifier. It's not on continuous values. What we are dealing with is continuous values. So, in fact, this work, my professor and I wanted to really take it up notch. Error metrics for data-driven simulation. Wanted to, he mentioned the word, wanted to publish it in Nature, creating sort of a compendium of all the error metrics, and then we just publish it, because there are a lot of them that we can put them into families of error metrics. So, but we couldn't get the time to do that. Now we have absolute errors, we have squared errors, we have log errors, we have correlation errors. Okay, so these are errors we can explore regarding regression. In classification, they have their own set of metric for measuring the performance of those models. So I don't want to belabor much point. We know these are the common ones when it comes to the absolute errors. We have the RMSE, the MAPE, and the explained variance. The explained variance is analogous to the correlation, coefficient of determination. How many of you know the R squared? The R squared, okay. So the explained variance is sort of analogous to that. Okay? Because we are dealing with nonlinear, we tend to use the explained variance. And then relative error. Relative error is also very important, because we want to see in terms of the actual values expressed with percentage, what's the percentage of we predicting the model predicting the actual values, right? And then the concordance correlation coefficient, towards the end of my PhD program, I stumbled it in one of the papers, and my professor insisted that we really present it. Why? And it's also in my PhD dissertation booklet or book. These are metrics that once you know them, this is basically related to health-related data, especially when repeated measurements are coming in. How do you validate? You can use the concordance correlation coefficient. You see that there is this correlation role between 2 variables, X and Y, okay, and then a mu, which are the means, right? And then, of course, sigma of X and sigma of Y are their respective variances. So if we have all this information, we can measure in a new method when repeated measurement is coming. How do we measure it against, let's say, a gold standard, if that exists? Does that make sense? So this is really important when we are talking about health-related data. Now let's get to the fun stuff, which is the models. We built a deterministic COVID vaccine model, a stochastic COVID vaccine model, and a behavioral model. Now, before I wrap up on the behavioral model, I'll say something so that you see how important these models are. First, the COVID-19 vaccine model. When we started the research, at that time, I was in Tennessee, and they hadn't rolled out any vaccination program yet. And so we're like, okay. And then I think right into December, we started thinking about what if we incorporate a vaccination parameter and make the model learn it and then fit it and see what's the impact of the vaccination on the dynamics of the model. So we kept some parameters. We also looked at the efficacy rate. How efficacious is the vaccination that is being rolled out in the state of Tennessee or across the United States. So that is also a rate, so between 0 and 100% or 0 and 1, as the case may be. So we fix those parameters, the efficacy rate and the vaccination. As my friends have talked about, the main parameters of this affecting the person, and then how we recover. So the recovery rate is very, very important. So we treat those as trainable or learnable parameters. Now the ENI, EINN. I said, so when we started working on this, we are in a team. I saw either Samuel or Emmanuel, you referenced G Long. Yeah, it's my colleague. We all started working on this thing together. Interestingly, either me or my colleague, we coined because we have been so used to PINN, physics informed neural network. So like, okay, we can, because we're looking at incorporating neural network with the disease model, we coined it to epidemiology because it's the same idea, right? They are all differential equations, so we just change, but it's a variant of, so we give credit to those original people who wrote the paper. They are in a Brown University. I was privileged this summer to present my work to the team, Professor Paul. They were really happy. I presented those to them. So without much ado, let me just explain what this was. So basically, we have the input and then the hidden layers where you apply the activation function, and then we have a portion for the residual. So the residual is what they talked about, the difference between the right-hand side and the left-hand. I really sincerely appreciate those who are still online. It means a lot. Okay. Thank you for your patience, everybody online. I want to move to the next. Okay. All right. So the key in designing an EINN is the loss function. So if you're able to get the loss function right, everything else will fall in place. So the loss function includes the loss in the data and the loss in the differential equations. And also you can incorporate the initial conditions as well. And so we see the E1, E2 measures, E1 up to E3 measures the difference. So you can see we are moving everything on the right-hand side and trying to find the difference, right? And so I use a very simple SIR model, the susceptible class, infected class, and the recovered class, okay? This is the algorithm. First, you have to initialize some input argument, the vaccination rate, the efficacy rate, beta, and the gamma. You have to give them. So again, this is all dependent on the modeler. And once you play with this over time, when you take a different problem, depending on the data, you can easily give a good initial values for that. And then specify the weight and the biases. Again, the activation function that is commonly used is the turn H, which has proven. You can you can apply the turn H to all the hidden layers, but then when it comes to the output, you can use the sigma. Now, this is also dependent on the way you pre-process the data. If you pre-process the data between 0 and 1, then you can make use of a sigmoid activation function for the output layer. And then you calculate the residuals, and then this is how your epidemiology will look like, the data, the SIR, and the initial condition. And then you can set the epochs, the number of time you want to train it, and then return the solution. After simulation, this is what we obtained. Our data was from the Tennessee Health Department, and we discovered that as the vaccination rates increase, so at that time, we're trying to make a case that, hey, policymakers, ensure that you are increasing the vaccination rates. Okay? So this is on assumption that if you increase the vaccination rate per day, okay, for the next 300 days, you should see the blue, which is the infected class, will in 46 days, you will see the infection come down. We'll pick up that, and then we'll begin to go down if you, first and foremost, if it has at 0 rate, we see 46 days. But I'll show you from 46 days, if you increase it to 0.5%, in 10 days, the rate of people infected is going to be 15.75. Now, from 0.5, you go to 1%. And then you can see the number of days it takes to peak. It was 11:10, but then as you increase it further to 10%, you see that it takes 2 days to peak. And then the number of people infected also reduces. Now, these are all simulations. We didn't get a time, and I remember Professor Moore was, in my first talk when I presented this, said we should collaborate it with the Tennessee data. We didn't really get time to explore that. But in my subsequent papers we wrote, we see that we're able to fit that model very well. Anyways, so this was to show or to confirm a known fact that if you increase the number of people vaccinated, the logical output is that you will see the percentage of people that are being infected reduce drastically. Does that make sense? Yeah, so that was the idea, to confirm a known fact. In this same paper, we did a very novel idea. I remember we got stuck somewhere, and then my professor had to take me for lunch and went to a very good place to have some pizza, not KFC though. The way they hype KFC in this Ghana here, I don't know. KFC is nothing in the US. Anyways, so it took me to a place and we had our pizza, and then after the pizza we started brainstorming And then all of a sudden this idea came that, well, why don't we do something like hybrid approach? Taking the ResNet and then the LSTM and trying to see how this model will behave in terms of performance. Again, in this instance, we are trying to learn the dynamics. Here, there wasn't any parameters being learned. So the paper played two roles, the vaccination and then just on the data. So what we did was to take the data and then use ResNet to scale the data. So if there were any errors or, sorry, noise in the data, the ResNet will smooth it out. And then we use the LSTM to do the prediction. So on that note, we're able to discover, as I said previously, that the group performs very well. So see all these models. We have the LSTM, the bi-LSTM, the group, and then ResNet LSTM, ResNet bi-LSTM, ResNet group. And you and I know that when it comes to RMSE, then the lower the value, the better, right? So if the error value is smaller, it means the model is better, or the approach is better. But with RMSE, also, if it's smaller, if the value is smaller, then I'm talking about the mean absolute percentage error. If it's smaller, it's also better. And then also for EV, which when Emmanuel presented his, the EVs were all in zeros, which means the model isn't better. There's about 98% better compared to, even though this is 3.856, we can see that relatively it's better compared to all of the others. But these two, RMSE and the MAPE, is what we made our decision on, maybe the EV as well. But we can tell that this is smaller than all of them. Okay. So this is how the hybrid approach works. You take the original COVID-19 data, let me retract. You pipe it through ResNet, get the output, and you take it back into LSTM. Yeah, that's the hybrid approach. The output from the ResNet proved to have smoothed out sort of any noise within the data, and now you put it into the LSTM. So it was pretty insightful. And this is a graphical illustration. We can clearly see from the RMSE and MAPE that ResNet Guru, I told you, Guru performs better. Even when you compare LSTM by LSM and just Guru on its own, can you see that Guru is small, right? Here also on the MAPE side, Guru is smaller. And if you combine it to Guru still perform better. So that is that. Now, cross-validation. So again, we wanted to have output. So not only did we give us a good accession of our model output. So like I told you, we did K-fold, 4 K-fold, 5 K-folds, the neighborhood of 4, 5, 6, 7. Again, prove that even though initially when K-fold equals 4, ResNet Guru didn't really perform better, but when we increase the folds, we see that ResNet Guru was doing better. This is K5, K6, K7. Like I said, the smaller, the better. You see that? That's smaller, but better. Now, here we're trying to prove that, hey, we can predict into the future, sort of help of the now and the past, we can extrapolate or predict into the future. And then we created some confidence interval. We're not so much interested in this part, we're interested in this part as far as this paper was concerned. Yeah. So somebody can take this work and extend it and use the latest the latest and the best type transformer to predict into the future. The LSTM, the Guru, and the PyLSTM, they all fail when it comes to long-term prediction. ARIMA not so good. I've tried ARIMA. ARIMA can but will fail some at one point or the other. So those are the limitations we found about the recurrent neural networks. Call it LSTM, PyLSTM, and Guru. These are the limitations. But with the advent of transform, which has really transformed the world when we have can be used. So if you get hold of my paper, somebody can really explore this as an extension. There are many extensions that we can do so, which is, and it keeps going. Now, we also thought about something called a stochastic COVID-19 vaccine model. We went from deterministic, and if you understand what deterministic is that it's expected that the model doesn't change over time, the inputs and everything are all static. But with stochastic modeling models, they have an inherent randomness that has to be accounted for. And why did we choose a stochastic model as an extension of our work from deterministic to stochastic? The reason was obvious. You found Ukraine war. Now we are, thankfully we are not in COVID, we are post-COVID now. We found many people trying to cross the border because the war-torn area, people are fleeing their countries. And so these are inherent randomness that the models do not capture. And so by using stochastic models, you are able to capture all these randomness, which also affect the level of infectiousness within the country. And so we consider that. So this and the fluctuations. There's a lot we can do with stochastic models. And so we wanted to explore what stochastic models are more meaningful in comparison to the deterministic models. And so we have two use cases here. One is without incidence rate and one with incidence rate. I couldn't get time to update. This paper has been published. Our second paper has been published and hopefully has one citation or something like that. And then we have the model with non-incidence rate, the rate of people get infected, right? This is a little bit complex, but we kept all the parameters like recruitment rate, natural death, recovery rate, and natural recovery rate, disease-inducing death rate, and all that. We kept all of them fixed. Our goal was to explore if increasing the noise here, we said, can represent all the influx of people coming into the country because of war-torn because of war or other environmental factors. So we want to capture that using stochasticity, the stochasticity within the model. And so the GS within the model is defined as this. It's a nonlinear incidence rate, and it's a proportional. The K is proportionality, H is the positive numbers, and alpha is some psychological effect. So what's the effect of, let's say, war on the spread or the psychic of the people, and how does it affect the spread of COVID-19? These were all back then when Ukraine war was very much fresh and COVID was still dying out. So wanted to see that impact. So our major goal here, we still want to have a consistency with the deterministic as well as the stochastic. And so we considered two scenarios. When the vaccination rate is very small and when the vaccination rate is higher. So 1%, 10%. And then with different noise, 5% noise, 10% noise, 30% noise, and these are all randomly chosen. And like I said, we fix these values. The values were chosen from this paper. Yeah, this is a kind of a long, very crowded, but I'm going to walk you through very fast. So again, you look at all your fixed parameters, and then you fix them. And then we use some sort of Monte Carlo, but we discretize the stochastic differential equation. Now, if you look back into the deterministic differential, it was pretty straightforward when you're doing the loss function. But you cannot do same for this because of the stochastic element. So you have to introduce a scheme. So this is called the Euler-Mariamar discretization. And that's a standard way of handling stochastic differential equations. So, and that's the leverage or the advantage that these deep learning models bring to the table. You can take the differential equation and then just, whether it's continuous or discrete, you can take that and embed that into your loss function to account for the, as it were, if you are dealing with physics models, it will account for the physics. If you are dealing with epidemiology, it will account for the epidemiology. So what we did here was, so this is the actual data. So we took the MSE of that, the discrete loss. So the discrete loss actually was found from the MSE here. So you're going I plus 1, you find a difference. I plus 2 and I plus 1. You find it, and then you sum, and then you average. When you do that, because of the sigma 1, sigma 2, sigma 3, you have to model it such that it account for that. Because if you change sigma anytime, it's going to affect. So we took the average. So we have n divided by n MC. So we are sort of doing an implicit Monte Carlo simulation within the SE and N. Okay. Now you combine these two losses and you have the loss. You have the loss coming from the data and the loss coming from the stochastic differential equation, SDE. Now, when you do all this, it goes through the same process. You update the loss, minimize. We implement this in TensorFlow, but although I like TensorFlow, I think I'll move to PyTorch now. PyTorch is much easier to implement. But the good news is recently I found TensorFlow 2 has been used to implement PINO, which I am eager to explore. So let's look at some simulation results. So here we have the actual data, And then we perturb the data with some noise, 5% noise. It's easy to do. Just some NP random stuff within a Python package, NumPy, and then we add it to the data. It to give you this messy looking data. So why do we incorporate that? I said earlier on, backtrack that wanted to account for the external fact, I didn't say external, but let me state that the external factors or forces that impact the model, which have not been accounted for in the deterministic sense. And so we perturb the data for both susceptible, infected, and recovered. Well, you and I know that if you have a real COVID-19 data, there's no susceptible term. So how do we find it? I was dealing with a simple SIR model. I knew the population of Tennessee, and so I do S plus I plus R equals N, and a simple algebraic equation. I'm able to find our change of subject. I'm able to find my S. So that's how simple you can find your S if you know the population. Okay, and then you perturb the data. Okay, interesting. Okay. Now, when the noise is 5%, it's pretty clear to know that both the deterministic and the stochastic is blue. The stochastic is able to at least somewhat fit the model very well, but the deterministic failed woefully. Okay, so this shows that stochastic models are able to account for the noise, which deterministic aren't. Deterministic models are not. Again, we increase, so we move from 5% to 60%. I did for 30% and others, but for the sake of presentation, we only showed extremely small and extremely large. From 5% to 60%, that's a wide margin. Again, you can see that at least the stochastic model was able to still see the pattern, right? Even though not being able to capture that very well, but it still get it. But then deterministic is way off. Can you see that? The red and blue, all right? So this is one of the things we contributed to research, that stochastic models. And then when I presented to this people at Brown, they suggested I did something like I quantify the uncertainty. That's also an area that we can extend the model to. It's a very broad, so many areas. Because we should be able to quantify the uncertainty that these stochastic models bring, as opposed to the deterministic model. They do not account for those. And so we have to account for that. So these are some of the results in a table form. So we kept the efficacy rate at 94%. And then we showed if we fix the vaccination rate at 10%, and then we change the different noise level, we saw consistently that the RMSE, the aerometric values, tend to be better compared to the deterministic. So it was pretty insightful, and the results were really good. Now I'll talk briefly about the GSI, which is the non-incidence rate. We also figured out that when it comes to the non-incidence, the model with the non-incidence rate, when the noise begin to increase, the SEIN was able to fit the model, close enough. Can you see that? With 5%, the SEIN was doing better. But it's still able to see the pattern, even when the noise becomes messy, very large, right? 60%, it's able to see the pattern. So this is where uncertainty quantification comes in. Now we can create this confidence interval bandwidth that is able to capture the noise. Because when you're dealing with stochastic models, you have to be thinking of confidence intervals because you have to average and all those things. So those are kind of extensions we can look into. Behavioral model. I'll be wrapping up soon. Now, this particular paper will publish it soon, but the truth is it came as a result of the National Science Foundation of the US. There's a foundation in the US that gives grant, and they are more or less the science. They do get federal fundings and stuff like that to help people to do quality research, because they rely a lot on data and what their scientific communities are telling them, especially the government. So they were like, okay, all the models do not really capture the behavioral elements, right? So we listened to a talk that presented these ideas to us. And so myself and my PhD advisor, we launched on it and we started working on something like that. There have been papers that have been published to that effect, but our goal was to use Thank you, everybody. Still staying online. We appreciate you. It's a simple SRM model, but the goal is I wanted to come up with a time-dependent model where this time beta, which is our transmission rate, is time-dependent, and then CT is called the compliance rate. So how do people comply with policies that come from the state or the government? So when the government says everybody should mask, that's a policy, or everybody should be vaccinated. Now, wanted our model to be able to capture this human behavior. You and I know this human behavior can fluctuate, right? But expectedly, we expect it to be quantified in terms of percentage. How well, whether 90%, whether most people are complying. And if most people are complying, it will go in line with the data fitting, right? If most people are complying, then we'll see the infection rate decreasing. So how did we get this 1 minus CT? So 1 means 100%, right? So if people comply, it's going to be CT at every point in time. If people don't comply, it's going to be what? 1 minus what? CT. That's how we got that. And since we're looking at the effect on the transmission rate, it becomes a product. So everything here is the same. We also introduced the death rate. Some very simple models, because what those stakeholders told us was that they didn't want any complex model. The models have been established. All these SRM models, they are there. But they wanted to capture the impact of, how do you call it, the compliance, the human behavior part. Okay. So in terms we're talking about time dependent, I think in the previous slide, I didn't talk about the basic reproduction number. So the basic reproduction number is basically the rate at which one person infect this and infect that, and it's the beta over gamma. So speaking of the same thing, since I'm dealing with 4 compartments, we're looking at effective reproduction number. So the effective reproduction number is a time varying parameter. There's not only static, it varies with time. And we can calculate what we call an updated data, because no longer do we have the initial beta, but we have an updated beta because it's going to be a combination of the length beta and then 1 minus C. All right, I'm going to wrap up those online. Thank you again for your patience. Now, this follows the same thing, but the only difference is that we introduce what we call a regularization parameter, and I'll show you why it is important. Because we wanted to penalize the huge losses coming from the data. And so these are some of the techniques, Emmanuel, you can do, okay? You can introduce some regularization parameter so that all the inability of the model to fit your data very well can be addressed. So that's one way you can also look into. Okay, some quick results. So wanted to explore this for some states, not only Tennessee. So we considered New York and Michigan. In that sense, we obtained some data within some within some time frame, and then we compared PINN with PINN. That is the original PINN and then the BINN. Although all of them showed that they are learning something between 0 and 1. Can you see that? Between 0 and 1 at these different times for these different states. But watch this in terms of the data fit and in terms of the impact. So when people are compliant, look at this. The red is the BINN output. Okay. When people are compliant, you can see that the transmission rate begin to fall. Can you see that? Same for New York. When people are becoming more compliant, it is expected that the transmission rate also falls correspondingly. You see that? Similarly, for Michigan as well, when more people become compliant, you see it goes down, right? So that's the expected behavior, and our neural network architecture did just that. How about the next effect? The next effect of the compliant is the impact on the effective reproduction numbers. Well, there was some stochasticity, which is expected as well, because again, this is at the time of the spread of COVID-19 in New York. In New York at that time was so messy. A lot of people were dying left, right, center. Even if they were compliant at the time of COVID-19 in New York, it was still messy. So this can be used as a proactive recommendation to policymakers. Say, hey, see what the model is showing. If you guys comply and comply and comply and tell them to comply with masks, comply with vaccination, you would see, even though you will see this stochasticity, but eventually you will see it going down. Can you see that? This is also going down. So what these stakeholders were interested in was to capture the behavioral aspect that traditional models failed to address. And then you see how the data filtered nice. Can you see that? Ima, can you see that? So ideally, the model should be able to help you fit your data well if you choose the right parameters. And if you do the right hyperparameter tuning, it should fit very well. And most papers that use PIN, most papers that use PIN, the data tends to fit very well. So if it's not happening, then something is not going on well with the model. And again, these are actual data I used. I didn't use any simulated data. I wanted to see of the two in terms of the BIN and PIN, which one is performing better. I call this part the computational analysis. And that's why the heading of this seminar is Computational Data Science. You should be able to analyze, go do a deeper dive into the model itself. So we considered the CPU time. We measured how fast BIN is able to train the model. And we discovered that BIN, although in terms of the CPU time minutes, it took 43 minutes. And guys, I use GPU. It's very fast. And I had to just allow it to run, and then I could go do my stuff. If you are using CPU, I can guarantee you that that would be even much more than this. Because I was privileged in my school. We had a computational resource. The bandwidth is very wide, and the speed is like, it goes very fast. So you're able to run this model. Now, in terms of the RMSE, the BIN was performing better and better and all that. We do all of these things to showcase if one approach is better than the other, okay? Yes, the computational analysis. So what if you tweak the parameters within the architecture? What happens to the error measure? So we considered this issue of using 32 and 64. And again, one could have chosen any, but I wanted to demonstrate the sensitivity, how sensitive is a change within these hyperparameters and the effect on the errors. And so we saw clearly that if you increase the neurons, so that's being deep. So the architecture can go deep when you're increasing the neurons. The architecture can go wide when you're increasing the layers. So from 5 to 6, 7, that's wide. But going deep is when you're increasing the neurons. Okay. And then we kept the epsilon. The epsilon is the regularization. So we did kind of try some bit of analysis, and then we wanted to see overfitting as well. We want to see the model overfitted or not. And clearly it shows that since these are going the same direction, overfitting is minimized. And then this is also an example of by increasing the neurons, increasing the layers. And then we went on also to see the regularization parameter. If you reduce it further, what it happens. So in conclusion, we provided the tools and the background needed to do the data-driven simulations. We also summarized the effect of increased vaccinations, and we established that if you increase the vaccination rate, holding other factors constant, or even if you vary other constant, it is expected that the level of infectiousness will reduce. That is a known fact, and our work proved that. We demonstrated the significance of stochastic models with varying noise levels for nonlinear incidence rates. We also showed the impact of behavioral and social factors. So, Prof, one of the things researchers are looking into right now is how do we incorporate the factor of education? How do we incorporate poverty? Especially in Ghana, I think this would be very useful. How do we incorporate all these factors and make the neural network learn them? So I think that could be a good research route to go. I think even right now, the NSF, National Science Foundation for the US, is still pursuing that because one thing about US is that they are very, very both proactive and reactive. So when something happens, they want to see what are the ways we can mitigate against. So they'll be making policies, laws, and proactively researching that if in case there is a future outbreak, we are ready. So they want to be able to have models ready that capture the human behavior part. Thankfully, thank God, in Africa generally, it wasn't messy, but America was. You'll be watching your news and every day. Yeah, it was scary those days. With my friends, my Ghanaian guys were in the same apartment. It was really, really scary. Very, very scary. So some of the future work, I really want to stress on the so our friends online. I want to stress if one has to do some collaborations, especially with the PINN. A lot of work has been done on PINN, and there's still a lot more being done. Okay, and then the spatial temporal epidemic models. That's also an area, and so that we don't limit ourselves. If you are from economics background, think of any form of differential equations within your scope. We can apply PINN and come up with a name for that. Once there's differential equations and you want to capture the dynamics that those different system of differential equations bring to the model, then you can use PINN. And that could be novel. I've not explored anything. I saw in my research, I saw something to the effect of stochastic informed neural network, SIN, or statistics informed neural network. So we can come up with novel ideas, think about something in economics, apply this, learn parameters, predict, or something like that. And then inclusion of more social and behavioral parameters is really an area we can explore. And then this has been done already, effect of masking or no masking on deterministic and stochastic models. And then Bayesian, because if you are thinking of stochastic, then you can also think of Bayesian approach as well. So on this note, I think I've taken a lot of time. I'll end here. Thank you, guys. Yeah.
So any question, those online, those in-house, any questions so far? No question. After listening to all that, I don't have any questions.
Please,
I think somebody has a question. Yeah, go ahead.
Okay, my name is Ezekiel. I'm attending from Kenya. Okay, my question is concern the stochastic model. So
Okay.
I don't understand how you defined the loss function, or how did you take into account the random component by
That's a good
when
one.
you define the loss function? That is my question.
Yeah, that's a good one. So can you see my screen, sir?
Yes, I'm seeing.
Okay. So we use the Euler-Maruyama to discretize. Are you familiar with the discretization approach?
Yes.
Okay. So we kept sigma 1, sigma 2, sigma 3 fixed at 10% or any random choice we use, like the 5%, the 10%, and the 30%. So with the random part, we encoded it, and because of that randomness, we have to take the average. Can you see that?
Yes.
We have to take the average of whatever. So we use 10 runs to capture that randomness. Does that make sense? So within the loss function, there are two things going on, right? Concurrently. We are capturing the random effect by averaging all the RMSC we are taking. So you see I1 equals NMC. Can you see that? So it's going from 1 through 10. and then it will take the average per each run, and then it will come and add it back to the loss function. Does that make sense?
Okay.
Yep.
Yeah, it is okay.
You're welcome.
Okay, so Ezekiel is my PhD student in Kenya.
Oh, wow.
Wow. University.
Okay.
He's working on stochastics, also depends.
Oh, nice.
Yes.
Yeah, I can share my code with you. Is that okay?
Yeah, it is okay. I will really appreciate. Thank you.
Okay, yeah, I have it on GitHub, so I can share it. Yeah.
Okay.
So you'll be happy then, right? So, but he's doing some kind of fractional stochastics.
Yeah, that'll be amazing. Yeah,
So
that'll be amazing.
So he's doing fractional stochastic with pins.
Yeah, that'll be amazing.
And we have some data from the mean of the base.
Okay.
So use that. That's what it is. All right.
Yeah, and then you can also extend it to maybe Bayesian pins.
Yeah, and I was going to actually talk about that.
Okay.
But just some weeks ago, I was in Senegal, and then I met someone from Swiss.
Okay.
Swiss TPH, Tropical Public Health Institute.
Okay.
And the guy, we spent about 2 days. We're just discussing patient inference and case. Yeah.
Wow.
Because actually a lot of the models on this COVID and malaria that we use, or people are writing papers on, that is not what they use to make the decisions. Yeah, the people who take the decisions here in Switzerland. So the things they think about, or they are using, the models they are thinking about and considering, that is where they use to make the decisions. So the ones we are writing here, we're just writing it, the opportunities out there. And this is actually the direction, one of the things to discuss with me, on Bayesian models. Because exactly you see that in pure stochastics, then you have an interval, a spectrum interval.
Right.
So although your line goes through, it's mimicking the pattern of the noise. If you give it an expectation,
Exactly.
then it captures the whole expectation.
Exactly.
That whole randomness.
Right.
What is exactly what the uncertainty quantification does is something that.
In fact, that was one of the direction my PhD advisor wanted me to go.
Okay.
But we were really stuck within time. In fact, I fell in love so much with UQ. They call it UQ.
Exactly.
Uncertainty quantification. A lot of papers also are being.
I mean, these are new directions that are coming up.
Yeah.
So, yeah.
So what's his name again?
So this Christian. He's from the Swiss
Okay. And then your student from
He's Ezekiel.
Ezekiel.
He's a Epidemic one of the PhD.
Yeah, Ezekiel, you
You
come
come here.
you come here, okay.
Please.
Yeah, Ezekiel, you can also explore UQ and stuff like that.
And when you come.
Okay. 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 Yeah. Any more questions online? Yeah.
In your presentation, you mentioned, so I saw a reference material about images.
Okay.
On dating and neural network for efforts.
No.
I've got to understand that it's applicable